get started. So the exponential laws are probably things that you're already familiar with, and they look very similar to the properties of the logarithm or the logarithm laws. So the first one, just to give you an example of what I mean, is this. If I have two exponential functions being multiplied together, so e to the x1 times e to the x2, let's say, then we add the exponents. And I should probably put a note up here that x1 and x2 are just numbers. And it sounds like someone's microphone might be on. I'm not sure whose it is, but make sure that you're muted unless you're wanting to ask a question or say something. Which is totally fine if you want to interrupt me to ask a question. But that's fine, Aaron. Okay, so we should probably discuss briefly where this comes from or why this is true. And this corresponds to the logarithm law for addition. Or the multiplicative property is usually what we call it. But when you multiply something inside of your logarithm, it breaks into addition. So log b plus log x. So if you wanted to verify that this property is actually true, this is what you would use to do it. Let's see. Maybe we can do one of those, but I'm going to finish writing out the properties. The second one has to do with the division property of the natural logarithm. So if we have e to the x1 over e to the x2, then we subtract exponents. And if we have a 1 in the numerator, or excuse me, a 1 here, so a 0 in the exponent, then we would get just an x to the e to the x. Let me start over again. How about I just write it down? That got a little bit mixed up. If we start with this, that corresponds to a 0 in the exponent here. That's how we would get a 1 in the numerator. So if you put a 0 here and a 0 here, on the right-hand side, you'll get e to the minus x2. So this is how you flip fractions involving exponents. You put a minus sign in the exponent. And then let's put property 4 here. This has to do with the way that you can pull exponents out of a logarithm, actually. So if I have an exponent e to the x1 with another exponent on it, then we can multiply the two exponents. And I use the letter R because R needs to be a rational number for kind of technical reasons that we won't get into. So it might be a good idea to discuss how these properties are true using the natural logarithm properties. So if I was going to start with this one, what I might do is start with not this function, or not this equation. I might actually start with the natural log of this side. And actually, I don't really want to work through this. This is something that you can read in your textbook, but it's kind of algebra. We don't have to worry about proving this. So what I really want to talk about today, I don't want to spend too much time talking about the exponential properties that you already know. We need to talk about the other exponential functions other than the natural one. Because if I have any number a greater than 0, then I can actually make a new exponential function with base a. And this works exactly like the natural exponential function, or essentially the same. You write it the same way. Like we have e to an exponent. Here we have a to an exponent. And we know how to use exponents when we have rational powers. So if you have like a 2 here, we know that's a times a. If you have a 1 over 3, that would be the cube root of a. But there are issues, and we talked about this a little bit last time, there are issues when you try to put in irrational numbers. Like, what if I had a to the square root of 2? How would we handle it? And the solution last time was to use the exponential function, the inverse of the natural logarithm. So we're going to continue with that. So an exponential function with base a is actually this guy. It's actually a natural exponential function, but with an extra factor in the exponent. That's probably quite confusing, but let me explain using some of the properties that we know. So here I have x, my variable, times log a. One of the properties of the natural logarithm was that we can move multiplication into an exponent, or we can move an exponent here to multiplication. So this can be rewritten this way. A to the x. And we know that the natural exponential function and the natural logarithm are inverse functions, so they undo each other. That means they cancel. And you're left with a to the x. So this is the relationship. So this is I should probably put this in quotation marks because I'm defining a to the x this way, so there's not really, this would be too circular. It would be a circular explanation if I'm not putting quotations around this, because this isn't exactly how it works, but this is the way that we should think about it. So if the properties that we know are true, and they are, then this is how it would work in theory. But in practice, we have to use this definition so that we don't have this circular thing going on. Okay. But we're not too worried about the laws of logic in calculus, so not super important for us. Are there any questions so far before we talk about the derivative? Okay, so this definition is important when we come down here to finding the derivative of the exponential with base a, because when I'm taking the derivative of this new function, I'm really looking at a derivative that we've already done before, or very similar to one that we've done before. I'm really taking the derivative of this natural exponential function. So instead of an entirely new function that we don't have any idea how to handle, we actually just have a simple chain rule problem using a familiar function. So the chain rule tells us to find the outer derivative, so the derivative of e to the x, or e to an exponent. And we get back the same function. This is the outer derivative. And then we need the inner derivative, the derivative of x times the natural logarithm of a. Okay, so this might look complicated since we have an x and a natural logarithm. Maybe you think we have to do a product rule here, but the natural logarithm of a is actually just a constant number because a is just a number that we picked, some positive number. So when you take the derivative, you're actually just looking at x and you're ignoring the constant. And you're left with just the constant by itself. Okay, and this still looks a bit messy. So this exponential in front is the same exponential from the definition for a to the x. So instead of writing out this complicated expression, I'm going to replace it with the function that we started with. So here is my derivative.
Here's something I found on Wikipedia. A directive is a legal act of the
Okay, sorry about that. The Alexa thing can wake up unexpectedly. Uh, it's muted now. Okay, and before we move on to some examples, I'm just going to write down the rule a little bit more clearly. So the derivative of a to the x is equal to a to the x power, but then we pick up this extra factor of the natural log of a. So it's very similar to the natural exponential because you do end up with the function that you started with, but instead of just that function, we pick up this extra factor. Okay, and once we know the derivative, we also know the integral because it's just the opposite. So the integral of a to the x dx should be equal to a to the x, and then instead of multiplying by the natural log of a, we'll actually divide. And we always have to add a constant. So put a plus c on the end. Okay, so there are two new rules to add to your memory. You'll need to use these quite often. These don't come up quite as often as the natural exponential function, but they definitely do come up. And before we move on, I want to take a look at some graphs. So let's switch over. Okay, here we go. So this is the same graphing tool that I used yesterday morning, desmos.com. And let's start by graphing the natural exponential, the one that we saw last time. So remember, the feature of this function is that it starts flat and then gets extremely steep. Okay, and now we can use one of these convenient online features that you can't use on a regular graphing calculator. Because on this Desmos website, we can add a slider for our base. So at the moment, my base is 1. You can see it here in the slider. And if I increase the base, we can see that the function gets steeper. And if I go to about 2.7, it should look really close to the natural exponential. So in this view, they're almost right on top of each other. And if I keep on increasing a, it just keeps on getting steeper and steeper. And this corresponds to, well, exponents. We know, let's just think of whole numbers. 2 squared, for example, is 4. So that would be down here. When you plug in 2, you get 4. But if you change your base to 3, and you plug 2 into your exponential, then you should get 9. So that's this point here on the curve, 2, 9. And if you increase it up to 4, we go all the way up to 16. So that's getting steeper. Where are we here? 216. And then it gets steeper and steeper and steeper. So 25 is all the way up at the top now. And if I go up to 6 and you plug in 2, you'll be at 36, and so on and so forth. So this thing gets quite steep as you increase A. And if we go the other direction, let's go back down to 1, the flat line. I can get it to stay there. So 1 to any power is always 1. So that's why it's flat. And if you start decreasing, we can see the curve starts bending. Okay, so I might have cut out there for a second. But if we decrease from 1, it starts bending the other way. So this is something like an exponential decreasing function. And then if I go too far, if I go to the negative numbers, then my exponential function doesn't actually mean anything anymore. What does -1 to the pi power mean? We don't know. So we have to stick with positive numbers. Okay, any questions over what these graphs look like before I close this down? Okay, guess not. Maybe everyone's asleep this morning. So now that we have maybe a mental picture, we know a little bit about the derivatives and integrals, we can start doing some examples like this one. So what is the derivative of x to the x power? Well, I can tell you what the answer is not. It's not x minus 1 times x to the, oops, excuse me. You don't decrease the power by 1 and multiply by the old power. So it's not x times x to the x minus 1. It's definitely not that. If you think about it, this is actually just x to the x again. So instead of using the power rule, we have to go back to the definition that we just learned for exponentials. See, here we go. So x to the x, we'll just put an x where a is. So e to the x times the log of x. And now it's a chain rule problem. We need the outer derivative. But the derivative of the natural exponential is just the natural exponential again. The rest of it will be a little bit harder. Not too bad. But we do have to use the product rule. Because we have x times a natural logarithm. So this guy, e to the x log x, we can just go back to our old notation, rewrite it as x to the x. And then this, take the derivative of the first piece, so you get a 1. And you're left with the natural log of x. And then you take the derivative of the second and multiply by the first. The derivative of the natural log is 1 over x. So you get an x over x, which of course is just 1. So this is what you get for your result. It's a tricky little derivative. It's very tempting to do this using the power rule, but it doesn't actually work because our base and our exponents are both variables. And anytime you have a variable in the exponent, you'll have to use one of these new rules. Any questions before we do the next example? So this next one is a bit simpler because we can just use the derivative rule that we learned a second ago. The derivative of a to the x is a to the x times the logarithm of a, the natural logarithm of a. But this one is a chain rule problem because we have this 2 in the exponent as well. So we have the outer derivative, that's the 5, leave the exponent alone, then you get the natural logarithm of the base. This is the outer derivative. And then the inner derivative, I'll write it out separate, is just the derivative of 2 to the x, or 2 times x. Which we know is just the number 2. And then we're done. Okay, any questions so far? Okay, so I guess we'll just keep on working. This next example is very similar, even has the same base as the last one, but now we're getting just a little bit more complicated with our chain rule. Instead of just 2 times x, we now have a very different function, secant of x. But we'll still just use the chain rule. So we have an outer derivative and an inner derivative. The outer derivative gives us the original function, with secant x still plugged in, and then the natural logarithm of the base. And then we need the inner derivative. So we'll have to take the derivative of secant. Does anyone remember the derivative of secant? Anyone? The derivative of secant of x is? I think I'll just wait until someone says it.
Is it tan x secant x?
Good, right. Tangent x times secant x. I was just about to call on someone by name, so you rescued your classmates. Okay, so since we're not in the room together, I couldn't tell if you were not answering because you just didn't want to, or if you didn't know the answer. Um, but if you don't know the answer, if you don't know the derivative of secant, now would be a good time, or maybe a little later today, now would be a good time to review some of these rules for trigonometry if you don't remember them. So review trig, derivatives, and integrals. We will see these a lot this semester, so make sure you know those. Any questions about these derivative problems before we do any integrals? Okay, so let's try our first integral with one of these exponential functions. So last time when we were doing these kinds of examples with a natural exponential function, you saw that when we had something in the exponent that wasn't just an x, we had to do a u substitution in order to finish off the integral. And that's the same way that these new exponential functions work with different bases. So since I have a minus x in the exponent, we're going to do a u substitution with u equals minus x. Okay, so if u equals minus x, we can find du. Take the derivative, you get a minus 1, or just a minus sign. Minus 1 times dx. And since we don't have a minus sign in the original problem, we probably want to move this to the left to make it a little bit easier to handle. So multiply both sides by minus 1 to get this. So now negative du is equal to positive dx. And that lets us finish off our substitution. Now we have 5 to the u and then dx becomes negative du. Okay. And then we can move this minus sign to where it would probably normally go, to the front. And then we have a very straightforward problem. Negative of the integral of 5u du. And in order to do this one, we'll just flip back to our integral rule for exponentials with different bases down here. So we'll just have 5 to the u over the natural log of 5. And we just have to remember to bring the minus sign along. And add our constant, so plus c. And we're pretty much done. The only thing left is to substitute back in for u. So instead of 5 to the u, we'll write 5 to the minus x power. Any questions over that integral? Okay, then let's go ahead and do the next one. Once again, we have something in our exponent. Here we're looking at the integral of 5 to the cotangent x power, and then we're multiplying by cosecant squared of x. So just like before, when we had something other than x by itself in the exponent, we had to do a u substitution. Now our u substitution is going to just be a trig function. Cotangent x. What's the derivative of cotangent?
Negative cosecant squared.
Good. Negative
X.
cosecant squared. So this cosecant squared in the original integral, which might have looked like it would give us trouble, actually just turns out to be our du, or negative du. Because there isn't the negative sign up here, we do probably want to move that negative sign to the left, just like we did in the last example. So what does this get us? Now we have 5 to the u, and then cosecant squared x dx becomes negative du. So basically this problem is exactly the same as this one. We just have a different u substitution going on. So we have the same antiderivative minus 5 to the u over the natural log of 5, and then add our constant, plus c, and finish off by substituting back in the cotangent x. Okay, any questions? No? Let's just keep on chugging along. So just like the natural exponential and the natural logarithm were inverses of each other, these exponential functions with different bases also have inverse functions. And they're logarithms with different bases. And the way that we usually write these are like this. So for any positive integer a, which shouldn't be 1 in this case, then the log base a, so you actually write out log and then a with x plugged in, is the inverse of a to the x. Okay, so that's nice enough as a definition. We can just define an inverse function because these exponential functions are one-to-one. We didn't really talk about that in detail, but if you looked at the graph, which we did see, you might remember that they would pass the horizontal line test. So that's what we mean here, that they're one-to-one. But what's the relationship between these new logarithms and the old logarithms? We should probably work it out. So what I want to consider is the inverse relationship. So a to the natural log, or not natural log this time, a to the log base a of x. And since these are inverse functions, they're going to cancel each other out. So we would just get x out of this. Okay, but now I'm going to do something that might look a little strange. I'm going to take the natural log of both sides. Okay, and the reason why I want to do this, take the natural log of both sides, is that one of the properties of the natural logarithm is that I can pull exponents to the front, and they become multiplication. So this is actually log base a of x times the natural log of a. So I've just pulled this exponent to the front. And once I do that, this nice relationship becomes clear. I can rearrange my equation, divide through by this natural log, and we get this. So the log base a of x is actually equal to the natural log of x divided by the natural log of a. So these new functions, which, well, they seemed like they were new, these new logarithms, they're actually my old logarithm, and I divide by a number. So really nothing new here. Any questions over that relationship? Okay, then we have just enough time to end with the derivative rule. For the natural log. Because we know this new relationship between the log base a and the natural log. I'm actually just taking the derivative of the natural log. That's why I keep on saying that. I might be I'm having a bit of a tongue twister, but that's the reason why I keep on saying it. It's just the old natural logarithm divided by a number. So the number we can just ignore or pull it to the front. And we're really just looking at the derivative of ln x, which is 1 over x. So this is the rule, which maybe I'll rewrite cleaner down here. Just combine the two fractions. Okay, and that takes us to the end of class. Didn't quite have time for my example, but we would just use this rule along with the old product rule that you already know in order to find this derivative. Does anyone have any questions here at the end of class?